In this session, we're going to examine relations and symmetry. And in so doing, we consider three types of symmetry. One of them is with respect to the x-axis, another is with respect to the y-axis, and finally with respect to the origin. For a relation that is symmetric with respect to the x-axis, if it contains any particular point, say x comma y, then this kind of symmetry indicates that we will also have a corresponding point, I suppose you could say, x comma negative y. In other words, being symmetric with respect to the x-axis means that a y-coordinate would change. To kind of think of it as a reflection type of thing. If a relation is symmetric with respect to the y-axis and it contains some point xy, then this kind of symmetry indicates that it will also contain the point negative xy. In other words, if I'm symmetric with respect to the y-axis, then the x-coordinate would change signs. And finally, if a relation is symmetric with respect to the origin, and it contains the point xy, then this kind of symmetry will lead us to the conclusion that we have the point negative x, negative y. In other words, for symmetry with respect to the origin, the signs of both coordinates would change to give a corresponding point. This actually gives rise to tests for symmetry. And in order to test an equation for symmetry with respect to the x-axis, we would replace y by negative y. If we want to test for symmetry with respect to the y-axis, we would replace, can you guess? X by negative x. And finally, to test an equation for symmetry with respect to the origin, we would replace both x by negative x and y by negative y. In all cases, if we end up with the equation that we started with after simplifying, then that indicates that the graph does contain that kind of symmetry. And these tests will constitute our examples for this section, the first being y equals 2x plus 3. So, first I want to test for symmetry with respect to, let's say, the x-axis. And to check that, we're going to replace, remember, y by negative y. It's kind of convenient to remember that whichever one you're trying to test for, you change the other one, unless it's with respect to the origin, which we'll see. So if I replace y by negative y and rewrite everything else, negative y equals 2x plus 3, there's nothing I can do to this equation that will make it look like what we started with. And so the answer to that is going to be no. How about with respect to the y-axis? As I said, you kind of switch up the letters here. So we're going to replace x by negative x and see if we can recover the original equation. And I see that if I do so, I have y is equal to 2 times negative x plus 3. And there's nothing that I can do to make this look like what we started with. So the answer is going to be no for that one as well. Finally, for symmetry with respect to the origin, we're going to replace both x by negative x and y by negative y and see what happens. Doing that gives us negative y is equal to 2 times negative x plus 3. And, well, if I simplify that, or try to, I get negative y equals negative 2x plus 3. Maybe I can try solving for y by multiplying both sides by negative 1. And I end up with y equals 2x minus 3, which, though close, is not the same as what we started with. And so the answer is no to that one. Ultimately, the answer to this question is going to be there is no symmetry here with respect to the x-axis, the y-axis, or the origin. Next, we're going to examine y equals 1 over x. Well, we're going to, again, check with respect to, check for symmetry with respect to the x-axis. And so if we replace y by negative y, then I have negative y is equal to 1 over x. If I, say, try to solve for y, I end up with y equals negative 1 over x, which is not what I started with, and so we don't see that kind of symmetry. For symmetry with respect to the y-axis, we're again going to replace x by negative x. And doing so is going to give me y equals 1 over negative x, which is the same result we had before and does not match the original equation. And so we're going to say no to that one. Finally, checking for symmetry with respect to the origin, we're going to replace x by negative x and y by negative y, giving us negative y is equal to 1 over negative x. As it happens, when I do simplify this, say solve for y, I end up with y equals 1 over x, which matches what we started with. And so this, the graph of this relation would be symmetric with respect to the origin. So that's what it looks like to succeed in one of these. Why don't you try testing y equals x squared for symmetry? Okay, so I'm going to check with respect to the x-axis. If I replace y by negative y equals x squared, I'm not going to get anything out of that. Checking with respect to the y-axis, y equals the negative of x squared. Well, that indeed becomes y equals x squared, which is what we started with. And so we're going to say, yep, there's symmetry with respect to the y-axis. Finally, checking with respect to the origin, we're going to replace y by negative y and x by negative x. And doing so gives me pretty much what I had the first time, which is negative y equals x squared. There's no way that I can make this match what we started with. And so we just have the symmetry with respect to the y-axis, and we're going to be satisfied with that. Here we have some more equations, starting with x equals y squared minus 3. Why don't you go ahead and pause the video and test this one for symmetry. So testing with respect to the x-axis, we're going to end up replacing y by negative y. And when I do so, the square washes away the negative, if you will. And so x equals the negative of y squared minus 3 simplifies to x equals y squared minus 3. And so we're going to say, yes, we have symmetry with respect to the x-axis. Doing so for the y-axis, I'm going to replace x by negative x. So I have negative x equals y squared minus 3. And this is never going to look like what we started with, and so that doesn't exist there. That kind of symmetry doesn't exist. And finally, checking with respect to the origin, I'm going to replace x by negative x and y by negative y all at the same time. And when I do so, I see that there's no way I'm going to recover this. Negative x equals the negative of y squared minus 3. No symmetry with respect to the origin there. Next, why don't you check for symmetry the equation x squared plus y squared equals 25. To test with respect to the x-axis, we replace y by negative y. So we have x squared plus negative y squared equals 25. And that square cleans out that negative. We get x squared plus y squared equals 25. And so, yes, we have symmetry with respect to the x-axis. Surprisingly enough, when I check for symmetry with respect to the y-axis and replace x by negative x, I again end up with something where the negative ends up going away, essentially. Negative x squared plus y squared equals 25 does indeed become x squared plus y squared equals 25, and so we also have symmetry with respect to the y-axis. Who knew? It should be fairly clear here that when I check for symmetry with respect to the origin, I'm going to replace x by negative x and y by negative y. The squaring eliminates both of those negatives, and we again end up with what we started with. X squared plus y squared is equal to 25. And so we have symmetry with respect to the origin as well. As a matter of fact, what you're going to find is if you have the case where you can say yes to any two of these, then you will always say yes to the third. It just kind of works out that way. The last two examples here. First, y equals x squared over x plus 1. Why don't you go ahead and pause the video and check this for symmetry. So checking for symmetry with respect to the x-axis, I replace y by negative y. And that's never going to look like what I started with. Negative y equals x squared over x plus 1. So no to that. Checking for symmetry with respect to the y-axis, I replace x by negative x. We have y equals negative x squared over negative x plus 1. Now it's true that in the numerator we're going to have just x squared, but in the denominator I have a negative x plus 1. And since that negative is attached to a term in the denominator, I can't do something silly like move it out front or anything like that. We're just kind of stuck with it. And so there's no way that this is going to match up with what we started with. And so we're going to say no to that kind of symmetry. Testing for symmetry with respect to the origin, we replace both x and y by negative x and negative y respectively. And I can clean this up a little bit, but I just end up with negative y equals x squared over negative x plus 1. And again, we have that negative as a term in the denominator. There's nothing I can do to try to, well, I can try. Maybe multiply both sides by a negative 1. Negative of x squared over negative x plus 1, which may look tempting, but if I decide to apply this negative to the denominator, it has to apply to the whole denominator. I would end up with y equals x squared over x minus 1. Both of these terms would change signs. Effectively, this negative would distribute. And since this is not what I started with, we're going to say no to symmetry with respect to the origin. And this is another one for which we're going to say no symmetry. Finally, why don't you test the equation x equals y over y squared plus 1 for symmetry. Testing with respect to the x-axis, we replace y by negative y. And when I do so, when I add and simplify, I get x equals negative y over y squared plus 1, which is not what I started with, so no to the x-axis. Testing with respect to the y-axis, we replace x by negative x, and there's no going back to where we came from there. Finally, testing with respect to the origin, we replace both x and negative x by y and negative y. We have negative x equals negative y over negative y squared plus 1. When I simplify this a bit, I have negative x equals negative y over y squared plus 1. And if I multiply both sides by a negative 1 to get x by itself, we get x equals the y in the numerator on the right-hand side changes signs. We still have y squared plus 1 in the denominator, and this matches the original equation that we had. And so we do have symmetry with respect to the origin. And you see this little page 4 out of 5 down here? It lied.